Hello, ladies and gents. This time we're going to talk a little bit about efficiency, and we're talking about energy efficiency. So when you calculate energy efficiency, basically what it means is how much work output there is compared to how much work input. There's two ways you can write this equation, and one is to say percent efficiency is work out divided by work in times 100 to make it a percentage, or you could say energy out divided by energy in, again, times 100 to make it a percentage. Both of these are exactly the same equation. I would personally write them both down. Kind of depends on if your head can translate work and energy well in your own brain. Otherwise, if you need both, write them both down. Now, this chart comes out of our textbook, and it lists the efficiencies of a whole variety of different things by percentages. So, for example, human body is only about 20% efficient when it's doing pretty strenuous exercising tasks like cycling or climbing. Swimming, highly inefficient. Very little energy goes in actually propelling your body. It's one of the reasons swimming is incredibly good exercise, because you have to do a lot of exertion in order to get any sort of motion out of it. Shoveling, weightlifting, steam engines, old-fashioned steam engines, about 17% efficient. This is not terribly efficient at all. Gasoline engines, about 30. Diesel engines, about 35. Now, those are not great numbers, and we've been having internal combustion engines for a very, very, very long time. But what that means is for every 1 gallon of gasoline you put in your engine, 30% of it makes your car go, and 70% is basically going to be lost. Diesel engine, slightly more efficient. One of the things that's interesting here is this helps explain why big long-haul transport trucks that handle big loads usually use diesel engines. They're a little bit more efficient, and because of that, they're a little bit cheaper to operate. Nuclear power plants, about 35%. Coal plant, 42%, which is kind of amazing. Electric motors, 98%. Fluorescent light bulbs, about 20%. Gas heater, about 90%. And solar cells are only 10% efficient. So this is a partial list, and we're going to talk some more about this efficiency thing. Now, I mentioned gasoline. If you buy, as I said, 1 gallon of gas, about 70% of it is going to be lost to heat. Now, as you may know, if you live in a cold climate, when you first get in your car on a frigid day in January, you turn on the heater. It is not hot immediately. Where does the heat come from that heats the cabin of your vehicle? It actually is part of the waste heat produced by the engines that they said, hey, we can use a little of that waste heat to actually heat the cabin of the car and keep the people warm. What happens to the other percentage of the automobile energy? Well, some of it gets to internal parts, idling and drivetrain loss and things like that. And basically it means that a vast majority of the energy that you put into your car is going to come out as heat. Kind of wild and crazy. Now, energy efficiency is a really, really tricky thing. If you want to get yourself a Nobel Prize in physics, come up with an engine that is only 50% efficient. If you want an internal combustion engine, we don't have one, and those have to do with the laws of thermodynamics, which we're not going to go into in great detail right now, but it is a hard thing to do, to convert combustion, burning of fuel, into kinetic energy or go power. But when we start talking about energy efficiency in things like vehicles, let's take a look at the full energy cost, because sometimes people don't look at things mathematically. They look, especially at energy efficiency, they look at it emotionally. And emotion is okay. It contributes to all the wonder of life. But let's look at this. If I have a typical internal combustion gasoline engine in my automobile, it's going to be about 30% efficient, which means 70% of all of the energy is going to be lost mostly to heat. So let's say you are a good human being and you buy a fully electric car, not a hybrid that takes advantage of some of the wasted kinetic energy, but a fully electric car. Now, there has to be a production of that electricity. The most efficient system we have is a coal-fired power plant, and that is 42% efficient. That means we're going to have a 58% loss. There's also electrical transmission lines. What do I mean by electrical transmission lines? Well, those are all those power lines you see next to the road. But on average, there is 8 to 15% loss getting the energy from the power plant to your home or city or place of business. So there is a massive amount of energy that's lost just in transmission of power. So let's kind of round this off and say, well, let's say we only lose 10%. Well, if I've lost 58% of my original fossil fuel energy, and then I lose another 10% due to transmission, that takes me up to 68%. The good news, electric motors are about 98% efficient. There's just not the heat generated, and so they only have another loss of 2%. Well, boy howdy, look at this. 70% energy lost, 70% energy lost. Why is this better for the environment in situations like that than this up here, when from an energy standpoint, this can actually be worse? You can have bigger losses if there are bigger losses in your transmission lines, or if you are generating the original electricity from something less efficient than a coal-fired plant. So how do we get around that? Well, the way we have to get around that as a species is we have to tap into things that are free. And energy sources that are free to humans are the sun and the moon. And that means water, tides, winds, and solar. And this is how this works. The sun evaporates water, puts it in clouds. The clouds rain the water down into lakes and rivers. That water then falls over power plants and spins turbines and makes electricity. This is cool. It's used everywhere from Niagara Falls to Hoover Dam to an awful lot of small power plants and dams all over the country. The challenge with this is expensive, big infrastructure. You got to have a river nearby. And when you build a dam, you flood lots and lots of area behind that dam. Wind is pretty free and pretty cheap. It is differences in atmospheric pressure and temperature. Winds have a tendency to move from areas of high pressure to areas of low pressure. And if those winds all by themselves flow, and what powers this? The sun. Then is a really, really great way to get energy. Challenge, each one of these wind generating power pole things costs a lot of money. Tidal power. Tidal power is using the gravitational effects of the moon. When the moon is directly above the earth, it is going to cause high tides. And then as it moves, that tide is going to move, and this will turn into a low tide. Water going towards the shore and then back away from the shore can be used to turn underwater turbines and generate electricity. The challenge, we have to build those. Solar power is not efficient. It's only about 10% efficient, meaning that 90% of the solar energy that hits these solar panels is going to be lost. Do we care very much? Not really, because the original source, the sunshine, is free. So if we lose 90% of free, hey, we are ahead by 10%. But again, we've got to build those solar panels. Energy in the human body. Human muscles are only 18 to 26% efficient. If you are a finely tuned athlete, you're going to be close to this end. If you're me, you're close to that end. What that means is every 100 kilocalories or food calories you eat, only about 20 make your muscles work. What do the rest of the calories do? Some of it runs your basic metabolism to keep you breathing and your heart pumping and things like that. And the rest turns into heat. And that heat is nice, and that's why humans are nice to snuggle. Now, one of the rules that deals with heat is something called the second law of thermodynamics. And we're not going to go into all of the laws of thermodynamics right here, but here's a really important big idea. And the idea is this. Heat energy always spontaneously flows from hot to cold. This is one of those big basic rules of the universe. This is the way it works. If I have a hot cup of coffee and I leave it in my office for a while, I come back later, it's going to be colder and the room is going to be a smidge warmer. A smidge, not a lot, but a little bit, because heat will flow out of high concentrations into the environment. If I have a bonfire, I am taking chemical energy from a combustion chemical reaction, generating heat. Heat is going to move out, and at the end of the evening's bonfire, where is all that heat gone? Well, it's made the air a smidge warmer, it's made the rocks and the earth a smidge warmer, but the heat has just flown away. So we've gone from a high concentration to a very, very low concentration spread all over. And low concentrations of energy aren't good for anything. They can do no useful work, meaning they cannot exert a force through a distance to actually do something when you have all these dribbles of heat that have been spread throughout the sky. Now, heat is a common end product when we're talking about energy situations. Let's go look at a couple things we've talked about in the past. I have a small child. The child does work by exerting a force through a distance. This is saved as potential energy. The kid slides down, whee, and potential turns into kinetic. But in this process, there is going to be loss, and the loss turns into heat. The slide is a little warmer. The kid's hiney is going to be a little warmer. The air is going to be a little bit warmer, and those dribbles of energy just off they go. Roller coaster, a lot of work is done taking all the people to the top of the hill. Save it as potential energy. Potential energy then converted to kinetic, kinetic to potential, to speed, up to potential, and back. At the end of the roller coaster, where has all of this work and energy gone? Most of it has dribbled off into heat. The coaster's a little warmer, the track's a little warmer, the air is a little warmer. You put gallons of gasoline in your automobile. Where does it go? About 30% of it makes your car go. The other 70% makes the air warmer, the car warmer, the brakes warmer, and it just dribbles away. So the common end product of most energy transformations is heat. Have you ever heard of perpetual motion machines? Perpetual motion machine is a machine that you get it moving and it's going to keep going forever and ever and ever. Here's the trick or the challenge. If you have motion, that means you have moving parts. If you have anything that moves, it's going to have friction. Now, the only places that don't have friction are when you start getting in the microscopic quantum scale. But anything macroscopic, big enough for you and I to do anything with, there's going to be friction. Friction is going to produce heat, and heat always leaves. Second law of thermodynamics. It's going to go from high concentrations to low concentrations. What that means is if you've got motion and you've got parts that move, you will never have a perpetual motion machine. So if your cousin Farley shows up and says, hey, invest in my perpetual motion machine, say no, and you'll save yourself a lot of money. All right, we will see you next time. Bye-bye.